to introduce our speaker today. Dan Ernst, as I mentioned, is a fellow Crayon from a long time ago, who is currently at NVIDIA, and he's the senior director of supercomputing systems technology. So with that, Dan, thank you very much for being here. I'm going to turn it over to you.
Great, thank you, Adnan. Appreciate the introduction, and again, it's great to be here in this community and see a lot of names that I'm happy to see, familiar with. So, hopefully, see how this works. Great. Well, thanks again for having me here. As Adnan mentioned, my name is Dan Ernst, and I'm the Senior Director of Supercomputing Systems at NVIDIA. I work on looking at what are we building, what are the technologies that we have at hand, and how does that interact with the supercomputing world and the world of high-performance computing and scientific computing. And so as part of that, I get to sort of sit in multiple camps. I get to sit in the world where we're watching the explosion of AI technology happen on one hand, but also in the world where I get to see and work with lots of researchers, community leaders who are building systems and doing scientific work that's also building new technologies, building new capabilities, and building new things for societal benefit. So it's an interesting place to look for where do those things intersect. I'll talk a little bit today about how that intersects, but also about how we think about building products and building systems that will try and address that hybrid need of how do we bring these new technologies all together in one place. From an AI perspective, we're in the middle of a giant growth curve, as everyone's well aware. But the technological reasons for that in the development of AI is three scaling laws, three techniques that have driven new capabilities with AI. The first one was the scaling of pre-training. We all knew about, you wanted to build a bigger and bigger model because at a certain point, the larger models would have emergent behavior. And we went from just sort of evaluating what a model would see to models being able to generate things, to be able to really, in some cases, reason about in a basic level and find the right things and generate outputs that reflected that in a way that was new, right? The ChatGPT type moment. Now we've moved beyond that in the last couple of years with post-training scaling. We have this general capability to have a conversation with generative agents. And now we want those to be refined and have specific domain knowledge. So things like I want a model that's able to reason about a specific scientific area or be an expert in what my company does as a helper agent. Those things can be done through techniques like fine-tuning, but also, more importantly, reinforcement learning is the case more recently, where that feedback is fed into model training from learning over time. And most recently, we're seeing this transition into test time scaling or long thinking models. And these are models that now, instead of just taking in a prompt and giving a response, they have the ability to internally basically introspect and have a thought process where they don't just generate once, but they generate something and then they feed that into a cycle where they're ingesting their own generations. They're thinking through things. They're generating things and then evaluating things. This is giving AI agents the ability to do things like plan. They can actually have a plan and then execute towards that plan in a step-by-step way, because they can take step-by-step, they can evaluate, they can spawn off sub-plans and so on. That long thinking is what's giving us, moving us quickly into an area of agentic AI, where AI doesn't just isn't just sort of doing a response, but has the ability to have do things, right? To basically not just react, but to have its own sort of active movement in the world. That's moved us into this agentic area. The next step in that is really about physical AI, right? So now that we have a sort of a level of intelligence that's able to reason about the world and what it might need to do, it has some agency in the world. How do we want that to be able to interact with the physical world? From a demand perspective, these three things have created a huge amount of volume demand for AI, right? For AI inference in particular, right? First of all, model training and model sizes were growing, and they continue to grow. They're not just doing straight pre-training. We're seeing lots of model architecture changes, looking at things like mixture of experts. And then the second thing is we're seeing this scaling for test time, right? This thinking process. And what it really requires is not just generating tokens once, but generating tokens and then using those tokens to think. And so the total token requirements to get an output are going up significantly. This is really a 5x tokens per year growth. On the chart in the middle, you can see, right, there was sort of a trend line, and this is the log scale of the amount of tokens to get to an answer, right? And we're seeing that really hit a ramp last year as people were moving to these more reasoning models. All of this is really combined to really get better answers, get more efficient answers, and the ecosystem overall is continuing to advance. And we're seeing cost of deploying these tokens go down, in part through things like model architecture. This is, again, a cycle where new capabilities arrive, those new capabilities are used to improve the models, improve themselves, and then move, again, make that capability available to everyone. What I'm particularly interested is in how AI scales beyond just LLMs, right? It's not just language. As I mentioned, as AI becomes agentic and has the ability to have some agency and do complete tasks, one of the questions is, how do we move into the physical world? So physical AI is something that's where we're looking at a lot. You hear a lot from NVIDIA about robotics, but part of that is really about understanding the physical world and then being able to do something in it. So a robot, you would like to interact with it by saying, go complete this task. And the combination of agentic AI and the ability to interact with the physical world is what would make that kind of a capability possible. To do that, and especially to do that in the world where scientific discovery is important, AI is attempting to learn the laws of nature, right? How can we help give data to and use data to build models that understand physics, that understand biology, that understand chemistry, and then how can we use that models to help advance our knowledge? A lot of this is happening in the open space, open models, where people are working together to build models, and I'll give you some examples today to reach those new frontiers of discovery. Just from our own perspective, we recently released a Apollo family of open models. This is a new family for us, which is physics-based models, right? These are not language models. These are models to really explain and understand structures, understand fluid dynamics. So if you want to, we have models for aircraft wings and understanding the airflow of an aircraft wing. We have earth science models looking at weather and climate. And then we also have things in the sort of the multi-physics space. We have worked with partners to build models that reflect fusion reactors, for example, and other things in the energy space. These open models, the intent is for them to be available for research, but also for industry, to be able to pull those models and use them, maybe not directly themselves out of the box, but to create a framework by which they can tune those models to their own data, to their own problem, and the underlying architecture of the models are there. The pipelines are all there, that they can have the shortest amount of distance to get something that's useful for their own purposes. All these are built upon our Physics NeMo framework, which is a training and inference framework designed for physics-based AI. So there's model training for AI physics, tools for your data creation and ingestion, and it's all built on top of a framework that scales across systems, and it's all handled by our own sort of tuning engineers behind the scenes, and that's all available openly. You can go pull that down and take a look at it. Okay, so I've painted a picture of models of all this growth and of models that are beyond LLMs. And we have this massive demand. How are we going to serve this? How are we going to build systems? And I come from a systems world. How are we going to build systems that can actually make good on these new technologies? And especially, how can we do this in the environment that we're all used to staring at, right? I mean, this graph is in every computer architecture presentation in the last 15 years, really, which is we're not getting transistors for free. Physics isn't doing us any favors like it was for a long time in the computer engineering world. How do we take an environment where the actual hardware capabilities aren't growing that fast and try and meet the needs of a 5x, 10x growth curve of AI infrastructure and of the types of problems we want to solve? The answer from an NVIDIA standpoint is we can't just rely on silicon. We have to build across the whole stack. And this is our continuous innovation pipeline, right? We want to be working across the whole stack, all working together, not just baseline compute stats or things within the chip, but the memory of that, the architecture of that, and how it all works together, how it's all connected together through things like NVLink or through other network technologies like InfiniBand or Ethernet. And then on top of it, of course, is software. And software means a million things, right? It's a lot of software. But most importantly, it goes beyond just I need a networking library. It's I need to understand and have libraries that are really focused on what algorithms can solve some of these problems, these technical scientific problems, and how do those algorithms, how can they be best laid onto the hardware that we're talking about? Okay. So it really needs contributions from all these levels of the stack to grow the performance and grow the capability over time. A really good example of this from a full stack view is Blackwell and the Blackwell platform. It is at the bottom, you can see, of course, it is 7 chips, right, in total. It's not just a GPU. It's not just GPU and networking. It's a CPU. It's GPUs. It's multiple types of network. It's scale-up network. It's NVLink. It's scale-out network of different types, depending on what you need, InfiniBand or Ethernet. It's the management of those networks. It's all the things that are needed to make the cloud capabilities through in these platforms. All of that has to be built, but also all of it has to be built such that it works well with each other. It can't be built in isolation. We have in the middle sort of the how do we put it all together stack. And we have everything from a compute node on the left to a scale-up NVLink switch, which provides a very high bandwidth in-rack fabric. And then on the right, we have, of course, the scale-out network that I think most of us would be used to, things like InfiniBand and Ethernet switches for the full fabric, all packaged together in the NVL72 architecture. On top of that, and just as important, is all of the pieces of software and platform capabilities that we make available. It's not just chip software, system software. It's not just networking libraries. It's the CUDA-X libraries in particular that bring out all of the different performance elements of different verticals, different scientific problems, different physics problems, different mathematical problems, and the design of those to best meet with what the hardware can produce. So let's build through these a little bit and look at some of these capabilities. The original Blackwell platform was built, again, for the era of trillion parameter scale generative AI. We are absolutely there. Modern models are multi-trillion parameters, and they're a variety of architectures. But we had a bunch of capabilities built into Blackwell in order to enable this, right? The obvious one is just the size and scope of this chip, right? And the 200 billion transistors worth of technology applied to one problem. We have the second generation transformer engine, which is a way that we enhance our tensor cores to automatically use precisions that are optimal for what is needed in the algorithm. We added the fifth generation of our NVLink technology, which has scaling capabilities up to 576 GPUs, although we're in productization only doing 72. The bandwidth of this capability is like 1.8 terabytes per second per GPU. It's a massive amount of bandwidth relative to what people might be expecting in a GPU to GPU connectivity. And the fact that you can do a whole rack of it opens up some really interesting capabilities. We have improvements in reliability. The RAS engine within Blackwell gives us a bunch of self-test capabilities to allow the GPU to make sure that it's in a good, healthy state. It has AI-based monitoring capabilities that allow it to identify if issues are arising and make adjustments ahead of time. We have new capabilities around security, secure AI, so full performance of encryption, so you can have encrypted mode, including on the NVLink in Blackwell, and we're the first GPU to enable a trusted execution environment through PCIe connectivity with hosts. Lastly, again, a decompression engine at very high bandwidth with the goal of having great analytics performance, and particularly the use of the CPU in this, which I've not talked about, the Grace CPU, and the connectivity between the GPUs and the CPUs, which can run at up to 900 gigabytes per second collectively, which is a very fast way to have a second level of memory for larger problems, and particularly data analysis problems. So this was what we built for Blackwell. I'll dig in on a couple of these. One is the transformer engine. Inside the GPU, this is a way of doing some intelligent precision management within. It's a cooperative. It's a cooperative technology. It needs both the hardware to support this microscaling of microtensor scaling, so you can go back and forth between precisions, and it needs some amount of support in the software stack in order to monitor what's happening with the different layers within your network. And the way it effectively works is as you're going through your processing, the software and the hardware work together to monitor what's happening, and they'll make changes of the precision back and forth between FP8 and NVFP4 in order to get the highest performance capability, but while still maintaining the right level of fidelity. This is a 2x kind of thing. It's pretty nuanced. It's pretty complicated. It's not simple to do this, and you can't do it without both hardware and software working together. Another technology is NVLink and the larger NVLink domain in Blackwell. And this is a technology that is making a huge difference in modern AI. Historically, if you want to deploy models, you have to deploy them in a way that they can have, for inference perspective, they can communicate very heavily within the domain between the GPUs that are cooperatively hosting that model. And so in the sort of traditional or prior Hopper generation, we had these 8-way servers, right? The HGX servers with 8 hoppers that were tightly connected through NVLink. And so if you had a model that fit on those 8 hoppers, it would be able to run very fast, have the highest rate of inference. But if you had a model that was too big, or a model that was more complicated, needed more space, then what you had to do was shard that model across multiple of these 8-way nodes. And the connectivity there you had was just Ethernet or InfiniBand, fairly slow relative to NVLink, really an order of magnitude or more slower from a bandwidth perspective. So in that perspective, it limited the types of models you could build, the size of those models. It limited the types of architectures you could build with those models because there was very limited connectivity between those nodes. In the world of NVL72, we have this high bandwidth all-to-all that happens between all 72 GPUs in one rack. So think of it as the same topology in many ways as the 8-way, but with full bandwidth all the way through 72 GPUs. That enables much larger models. We talked about Blackwell being designed for the trillion parameter AI. It also enables a lot more cooperative model environments. So think things like mixture of experts models, which are, you have different ports of the model, which are experts at different things. And so you will only highlight and light up certain parts of it in certain queries, which you may not know depending on what the query coming in is. And so those models, again, need a fair amount of cross communication between all the sub pieces, the different experts is in the model. All of these things lead to this type of architecture giving a really massive uplift in MOE model inference. So you may have heard of recently what was originally called Inference Max by SemiAnalysis. It's now called Inference X. I think they changed the name a couple of weeks ago, where they do evaluations of inference on different models, and they show it in the context of what they call a Pareto curve. And so the y-axis on these curves is how much total token throughput can I have? In this case, it's per megawatt, right? It's per power, so this is efficiency. And on the bottom, the x-axis is what is the tokens per second for a single user. And so you can think of this as how fast can I get and how large of a response can I get and how quickly can I get it as an individual user. There are many different points along this curve. You can configure your inference engine to optimize in one direction or the other. And where you are really depends on what your goals are. Do you want a really deep answer, and do you want your model to think very deeply? You might want to optimize for tokens per second for a single user, because then it can internally think faster. Alternately, from an economic perspective, you want to optimize for getting the most tokens out of your GPU investment you want if you're an AI factory. And so you might want to push up the y-axis to try and get better tokens through, total tokens across all users as high as possible. All that said, if you look at GB200 relative to H200, that there is a 10x performance uplift. Is a gap of 10x between the Pareto curve of H200 and NVL72 GB200. That capability lets people, again, drop the token cost by a factor of 10 or more tokens for less power and less money, right? So from an efficiency standpoint, we're going to get more intelligence, 10x the intelligence per watt. Right, so as we're deploying new AI factories, it's a big uplift. If you look at GB300, there's a few extra enhancements. There's a larger memory size. There is again an enhancement to the tensor cores around FP4, and those combined give us another 5x between where we were with H200 and GB300, and in fact move the curve further to the right overall. So this is what this co-design, this full stack co-design can do, right? Because the GPUs alone would not get this, right? The GPUs with the networking, with the software, the cooperative transformer engine, the NVL72, all of that together is what drives performance on actual inference, right? From technology perspective, we do spend a lot of time looking at precision. And so NVFP4 is a capability a new data type that we developed in collaboration with a lot of our model partners. And it preserves accuracy but boosts performance. That's really the goal whenever you're dealing with precision is, can I get the same accuracy in my model, but get it faster? That's really the goal. And so far we're seeing that with NVFP4. If you look at GB300 in FP8 mode versus NVFP4 mode, it again gives us another boost. That's part of that boost, that stack up. And again, if you look at just MLPerf, the growth of doing pre-training, right? It's not just inference, training as well. All of these capabilities are stacking up to give a big multiplier. We have done work to get NVFP4 as we have successfully trained models with NVFP4. There are papers available to go check those out. Many people thought it was not possible. They were like, well, we do FP16 or FP8 for training, FP4 is for inference. No, we've shown you can do it. And there are again, performance reasons that it might be useful. So these technologies are not just limited to AI-based technologies, right? One I want to highlight from a different domain is we are spending a lot of time looking at precision for numerical computing, right? Things like scientific computing, engineering, those types of applications. This is sort of a virtual desktop of our numerical library sleeve. And a lot of what he's looking at these days are around using all of the capabilities of a GPU and applying them to problems that normally wouldn't use them. And so things like the use of lower precision tensor cores to actually run high precision math by building up high precision operations out of low precision operations. Things like the Ozaki scheme for doing gems like dgem on using things like int8 tensor cores instead of a full FP64 implementation. We've done implementations of that. We're looking at mixed precision algorithms to feed into our libraries. And then we're also looking at tools. It's not just, again, about what do the libraries do? It's how do we enable developers to do new things? So we're looking at things like tools for how do you investigate the precision needs of a numerical application. Just looking at the opportunities here, if you look at a mixed precision iterative refinement solver, so what that means is you take and you do a solver, most of it in something like FP16, but then you do iterative refinement at the end to sort of build it back up to FP64. You can get a lot of the performance benefits of mixed precision while still ending up with an answer that's within the acceptable error. We've done a lot of work on these types of solvers and have integrated them into some of our cuSolver library if you'd like access to that performance, right, that's available to users. Similarly, with things like emulation, like Ozaki scheme, we've built a version of emulation into our cuBLAS library, and so anything that does a double precision matrix multiply or a single precision matrix multiply can just call SGEM or DGEM, and if we find that we can get a benefit from this technology and this capability, these algorithms, we're going to use it, and it's not something the user has to directly interact with. What's really interesting with this technology is it provides a 2 to 3x boost in performance per watt at the chip level for doing things like DGEM or SGEM. But if you think a little bit about your application and you need a little less precision, maybe you didn't need FP64 entirely, maybe you just needed like FP50 or FP48, you can actually tune that with an environment variable very easily and get additional gains in performance and have a direct knob to be able to do that. This applies to really GEM algorithms only, but it's an example of the type of thinking of how do we build across the whole stack to build capabilities that users are going to find useful and drive new performance levels. Okay. Those types of capabilities are being investigated, not just at the algorithmic level, but we are trying to learn about what's needed at the vertical level. And so across a number of domains, most of which, and this is like one of Jensen's favorite slides to show in his keynotes, these domains are not physics or genomics or signal processing, whether quantum chemistry, all those types of things. We are working to build and integrate with libraries across the world and understand what those need, not just to make better libraries and make performance more available to users, but it's also how we learn. And so by looking at those libraries and working together with partners in the community, we can learn what those libraries need algorithmically. What are they trying to do? And we can bring that into our own internal development cycles and help drive actual changes to our hardware and our platforms, right? That's how we do those evaluations, right? We start from the applications, we try to understand what they're doing, and that helps guide us in what we want to be building into the future. From a supercomputing perspective, this has been a pretty successful model over the years. And if you go look at things like the top 100 supercomputers out of the top 500, they were all CPU systems even 10 years ago, more or less, most of them. The ones that weren't were oftentimes odd, but they were unique. They were new accelerator systems, and they were sort of a new thing. It really only was 14 or 15 years ago when Titan arrived, and it's only, I think, 18 years since the original Tsubame system that did GPUs in Japan. This curve has continued to accelerate, and in the most recent list, we're well over 85% of the top 100 being GPU or accelerated systems in the whole, right? It really is a more performant, more efficient architecture for any sort of throughput computing. Any place you care about high performance and high throughput, GPUs as an architecture are going to deliver a better result. And the applications have followed this. It's not just because systems are built, right? There's a massive list of applications in the HPC world. Some of them are research codes, but there's also a lot of codes that are of course, ISV codes with the engineering community. All of them are eventually and in part either fully ported or on their way to being ported to GPUs and being able to be run on these types of accelerated platforms. A couple of just flagship examples. Maybe most people here are familiar with the Gordon Bell Prize. The Gordon Bell Prize is a sort of an award given every year at supercomputing, focused on sort of new capabilities, people that do runs of scientific computing operations that have really never been done before, and at a higher resolution, at a larger scale, solving new problems in novel ways. And there's sort of two, there's the main award, and then there's one that's really about sort of climate. If you look at Gordon Bell, there's a couple of examples that were run on NVIDIA systems, at least in part. And one of them is an extremely high resolution climate model, 1 kilometer resolution whole Earth model that was run on Jupiter in Jülich in Germany on their Grace Hopper Exascale system. And this is incredible, one of the most detailed and complex climate simulations ever to be attempted. And it could only be done on a system that at that level of scale and resolution. On the right is another and maybe a little more creative attempt, which is a tsunami real-time warning system. And the idea is when there is a seismic event, you want to know whether a tsunami may form. And if you want to run a high-resolution simulation of that seismic event, the amount of time it takes is long enough that, in particular in places like the Pacific Northwest, which are where a fault line is very close to shore, you don't have time to run a simulation to tell you the details of what might be coming. You'd like to know very quickly. And so these users, these researchers built a model based on many simulations. They used that data to build a model such that if a seismic event happens, it can do an inference into that model to get a very close estimate of what the expected tsunami activity might be in effectively real time, which means you could have an entire warning system basically based off of this prediction. So that's a case of using a combination of AI technologies and simulation technologies to build a new capability, right? In computational engineering, we are seeing accelerated computing take off. And this is, NVIDIA is right now partnering with a lot of different ISVs in this space and engineering companies. You can look at something like a Total View, Star CCM Plus that we're partnering with Siemens to develop, and even down to our own engineering work, where we're working with people like Cadence and Synopsys to help accelerate their tools for EDA for our own purposes, for our own designs. But these are also being accelerated with AI physics, as I mentioned earlier. There is a partnership with Luminary Cloud, who is in service of Northrop Grumman in this case, where they were looking at designing a rocket control nozzle with the idea that it would they want to look at different designs for this nozzle, different actuations for this nozzle, and understand what the output and the result would be. To simulate all of those cases is very intensive. And so what Luminary did was do a sweep of simulations across different configurations that was enough to train a model, and that model, when given a configuration, could output a predicted outflow of the nozzle in effectively real time. What that allows is a designer to manipulate and try a bunch of different options, see what the results are at a very high level, and then as certain cases appear to be promising, then they could go back and run a more detailed validation simulation. But the AI model itself was within about 5% of the physics ground truth in terms of its output. And so it enabled this whole design space exploration. It expedited that exploration enormously by using AI physics in combination with the simulations they were doing. Really exciting model. We're seeing a lot more of that kind of thing. Use simulations to generate data. That data can then be used to train a model, and that model can be used to greatly accelerate the design space exploration in which you might need that simulation in the future. We have some particular partners in sort of the national lab space. I'll call it Los Alamos as a case that they're doing some very interesting AI for science work. One of them is very language model based. So they're doing hypothesis generation, and they're looking at fusion, right? And sort of fusion, the real physics in the inside of fusion, looking at things like NIF, the designs to do the National Ignition Facility. What are the types of designs that would have successful results there? And they have trained an LLM to understand, effectively start from a baseline LLM, and then they refine that, they fine tune it, and they bring new. They gave it papers, like 1.5 million open science papers. They've generated a bunch of tokens in Q&A with experts. They fine-tuned on like 100,000 papers that were very specific to fusion. And the ultimate goal was to really solve some of these long-standing problems by getting better experiments, having this language model be able to have a conversation with the designer and help guide towards a good designs, right? What are the areas that it think would be promising based on all the body of research in the past? The other one they're looking at is some molecule design. And this molecule design is really about binding with certain types of metals. highly effective treatments for certain types of things. This can be a drug discovery workflow. Lionel's working on building a agentic discovery platform. So this is an agent that is trying different options and then doing a combination of so AI prediction and then simulation to verify different options for these molecules, right? To try different, like, think this might be promising, goes, runs in simulation and verifies, and so on. Those types of capabilities are, they've already found, using this workflow, new molecules they had not seen before, and new candidate molecules with superior things, superior binding energetics, right? So the idea that you're getting the agent to do this sort of initial condition setup, hey, you should look over here, hey, you should look over there, in a way that gives you a pretty high rate of hit, is a new capability. And again, this is where agency helps a lot, right? The agent can really do all this in a workflow by itself. It doesn't need a lot of interaction with scientists. And one other area I'll highlight is really around quantum computing, and we're doing a lot of work in quantum, in understanding how systems work, in modeling quantum systems and simulating quantum systems, and then in trying to build capabilities for people to interact and have classical systems and quantum systems interact. Just a couple of examples of what kinds of research has been done on platforms that we've helped with. One is, again, around Jupiter. I showed the climate simulation from them earlier. They also did a 50-qubit, excuse me, hit the wrong button there. A 50-qubit state vector simulation, which is a massive simulation. Like the qubit count is not, it's not a linear growth in simulation time for qubit count going up. It's much higher than that. And so this capability of both having a large system, also having a large memory with the Grace Hopper architecture, again, that high bandwidth link between the CPU and GPU, let them address a larger problem. On the right-hand side is a fascinating work done at Ernst, where they actually simulated way down at a sort of micron level the electrical properties of a quantum processor. Right, so this is looking at the sort of like watching a QPU, watching a quantum processor breathe, right? It's the electrical properties as it's happening. To me, what's interesting about these two is they really point a direction towards design of quantum computers. So on the left, you have sort of like a very early version of quantum logic simulation. And on the right, you have a very early version of sort of quantum spice models, if you want to think of it that way, right? The electrical properties of something. And so in the future, as we're moving forward with quantum computing, you would expect this is the early version of like quantum EDA, right? Design automation. And so watching these tools and how they develop is pretty exciting to be able to see. All right. So overall, that's how we've approached this, right? We've got, in the scientific sense, we got simulation, we have AI, and we are starting to see work in quantum, particularly at research centers. And we're throwing a lot of technologies at all these areas and building them up in a full stack way. Models, architecture from chips to systems, evaluation and working closely with application developers, and then building the library glues that's going to bring performance across the whole stack to everybody. So that's what I have. Happy to take questions.
All right. Well, thank you very much, Dan. So we've got a few questions. Let's get started. One is from Dermot Buckley, who he's referring to the scaling chart that you had, towards the beginning of the presentation. And his question is, the clock speeds seem to plateau. Is that expected to be a pretty hard blocker in the coming years?
Yes, and from a raw physics perspective, clock speeds have not really moved in a good decade, maybe two. The reason for that is to increase clock speeds in silicon, typically you also have to increase voltage. And if you understand how power happens, power scales, power goes up quadratically with voltage. And so if you have to increase voltage, you are, by definition, increasing power significantly. And pretty much every design in those last 15 years has been trying to optimize for performance per power, because power tends to be the limit of how much we can shove onto a chip. It's not necessarily just area. What it's the performance, it's relative to the total power. It tends to be more efficient to do more things, right, width, at a slower speed, because width is linear, but power is, and frequency is quadratic in terms of power.
Okay. All right.
I don't expect that to move much.
All right. So whilst I'm doing this to the audience, feel free to put in your questions that you might have. The other questions from Bill Turner, and he states that his understanding that RAM is presently the hindrance, is that being addressed?
We've made a lot of progress on memory, and this is the case, by the way, from coming from a background that's more high performance computing and simulation. Like, we've cared about memory forever. That's what we've been designing around. And just as a piece of background, I was the memory architect at Cray for a long time. That it was a core piece of what we were trying to do. It turns out that's an area that sort of simulation and AI have a lot in common. That RAM is very important to those workloads. If you look at Hopper to Blackwell, the memory performance of HBM went up by a factor of 2, depending on how you measure. If you look at Blackwell to our newly announced Rubin platform, it went up by another factor of 2 or more in terms of memory bandwidth. Capacity is also growing. That causes some consternation, because with capacity also comes cost, right? So that there's a trade-off we have to walk there. But we're absolutely investing heavily in memory, and we, because of the amount of HBM that we use, we spend a lot of time with memory vendors, optimizing, trying to push corners, make things go faster. We're also, from an architectural standpoint, doing things within the chip to enhance memory performance. We've done memory compression cases that help improve bandwidth through compression. We're constantly looking at different modes of operation of the GPU that might make memory performance faster. So yes, it remains a core limitation. In some cases, we are actually starting to see that we need to fix other things, because memory has gotten fast enough that it's exposing it, right? So that the trend lines for memory performance have gone up very high the last few generations. We're now starting to run into other bottlenecks, but there's still people asking for more bandwidth, right? It's not universal.
Right. Okay, and I had one question related to that. And, with the GB300 and the NVL72, the rack acts as a single node with a unified pool of I think 20 terabytes. From a programming model, do you have to do anything in order to be able to access that? Do you have to rewrite your code?
So let me first clarify the model, how it actually runs. So for GB200 or GB300 NVL72, each 4 GPU tray is its own OS instance, so it's its own node. And so you have 18 different nodes in the tray, but the GPUs are all connected on the backside with this memory fabric, right? This NVLink memory fabric. How they tend to interact and how you would use them is within your kernels that are running on each of your trays. There are effectively collective domains that are set up that use that NVLink network. They use the low latency property of the memory, and as a user, you would interact with it just through using collective calls in something like Nickel.
Okay. All right. Okay.
Or there are models to do NVSHMEM, which is effectively a PGAS type model,
right,
that you can use within that rack. But for most of the AI folks, the way they're interacting with it is collectives libraries.
It's collective. All right. Okay. One more question from Konstantinos Evangelos, I think. With the hardware emphasis being placed on tensor core low precision flops, the bet appears to be that either one is compute bound and the computation can be done at lower precision, or use the Ozaki scheme, or if it's FP64 but memory bandwidth bound and a low FP64 peak does not matter much. I guess this is the general sort of conversation we've been having, like, the lower precision favors, for AI training and inferencing. But we're all HPC folks and we want more precision. So, what are your thoughts on that?
Yeah, let me address that. So from a perspective of tensor cores and low precision, part of the reason that the growth has been there so heavily, there's two reasons. One is because people will say, oh, well, AI uses low precision, so you're going to do more low precision. Okay, that's part of it. But the real, I would say, technical reason is because doing lower precision is far more efficient. If you can use it, right, from a hardware perspective, it's like a quadratic improvement, right, from lowering precision. And so we've done work with these model developers, and they've been like, yeah, we can do the next one down. We work to find the gaps of things that might need to be filled, like NVFP4 is a great example of that. We worked with them to design, well, if we want to go down to 4-bit, it has to be there's some requirements about what that 4-bit needs to be, right? So that's the technical reason. From a physics perspective, right? Designing a chip, you will get way more performance if you can use low precision. That said, I work with a lot of people that are numerical analysts and scientists internally to NVIDIA, and we understand that, yes, there are absolutely simulations that need FP64, they need FP32 heavily. We have done a lot of work to understand, as I said, working with the applications through the libraries, how much do we need? What's the requirement level there? And if you are doing a gem, like a DGEM, which really would correlate with the type of architecture you have in a tensor core, right? It's matrix, matrix, dense, matrix, matrix multiplication. There are some applications that use that, and for that we would use, our cuBLAS library using algorithmic schemes to get the most performance out of that we can, right? So Ozaki is an example. On the other front, many of those applications and most of the sort of simulation applications you look at don't use DGEM, they're doing sparse matrix vector, for example. And in almost every one of those cases, they need FP64 precision, and so our hardware will have it. Just as a special note, GB200 has FP64 at a full rate. GB300 does not, because it was emphasized as sort of as an inference optimized GPU. So just be aware of that. Rubin has the full hardware implementation again, to be clear. But we did evaluate, like, the applications doing sparse matrix vector, they need FP64, but the amount they need is not very much, because most of it is memory bound or bound by other things within the architecture, right? This is really part of the outflow of this Moore's law chart, right? We can put capabilities down, but we're in a resource constrained environment, and so we want to put down what we need to make sure we get the performance to go up, but we don't want to overdo it, right? Just to chase a marketing number, right? That's the analysis that we have to do internally, and we continue to do. So,
right, yeah. And I can appreciate that. Well, unfortunately, we have run out of time. Again, thank you very much for the very interesting talk, Dan. This was extremely helpful, and I'm sure our audience found it helpful as well.